Yeah, I don't know. Oh, maybe sometimes power helps, right? You need to switch it on. Okay, I think that's all. Stupid. Power. Okay. Well, that was easy but stupid. Okay. Let's get into some things. Yeah, before I begin, there was a small error in the homework, latest homework. And what's error? And very fundamental. But it's a typo at the same time, since I didn't look into the homework problem. So have you guys started homework 3? You finished it. Okay, so there was a very bad error on my part, embarrassing error. It says bracket structure on top, but the problem is not the problem that you do is not really the bracket structure. So it's a well-defined problem of a row hanging and what's the shape of the row, but that's not bracket structure. So I thought I wanted to give the bracket structure problem, but I cut and pasted another problem from my. I just maintained notes. So
aren't those canaries?
yeah, that was a cat. Yeah, so that's just a cat. Bracket structure has the solution as a cycloid. What's a cycloid? So, have you guys heard of cycloid?
I think we did a problem with one of those earlier on a quiz problem, maybe.
Yeah, probably. Yeah, it comes.
Isn't that the?
Yes, exactly. If you put if you are in the night, you have a bicycle wheel, and you put a small light on one of the rim of the bicycle wheel. So think of a bicycle wheel and have a light. And imagine this is dark, and this will have a path, right? If the bicycle was not moving, so if it was just moving or just going around this axis, it will go in a circle like this. But now think of the center of the wheel going with a velocity v. Right? Then what happens is that as this rotates, this will actually go like this. And then keep rotating. Right, so that's called a cyclone. That's a solution for a bracket structure problem. So what is a bracket? Yeah, we'll talk about bracket structure problem in the class. So I was thinking give it as homework. Class. That's historically bracket structure was the first ever a problem that was solved using the functional derivative. You don't call it fun. At that time, it was just calculus of variation. Even now, it is called calculus of variations. The functional derivative is a tool that is used to do that. And I think from what I read, I think just the standard simple pages, apparently it was Bernoulli who gave this problem. Remember, calculus started right at the time of Newton, and Bernoulli was a contemporary. What's the word? Contemporary meaning? Colleague? Is that who lived at the same time? Is that the right usage of the word? Contemporary, or just another guy who lived, but an important person, like very influential. So he came up with this problem, and he posed it as a challenge problem, apparently, in an article, like, let's say, equivalent of a journal here. And the story is that Newton read it and he did it overnight. And that is probably, you know it because of Newton has been very well researched. So the people really looked into all his documents, and apparently he did it overnight. That's the idea. So that gives credit to Newton, but yeah, of course, Bernoulli had solved it before. So that's the first problem done using these methods. So, and it's a nice, it's also a thought-provoking problem. I think the way you pose it is, so let's say you have an inclined plane and you roll an object and it takes a certain amount of time to reach that. And now you ask, is that the shortest way? Is there a faster way to reach that? Especially sometimes you say that, okay, what if you have a trajectory like this? And the argument typically is that, oh, if you go this way, you don't gain much velocity. Here you're gaining a lot of velocity, so you gain a lot of speed. So that means you're able to go faster, but then you have to go along a path. So that's the compromise you take. And when you go by the velocity part, you would say that, oh, I want to make it steeper and steeper so that I can gain faster and faster velocity, but then you have to go faster or go deeper. So there is an optimal path here in between this straight line and all these paths, and that turns out to be exactly the cycloid. So you invert a cycloid, and this is part of a cycloid. Think of this as going all the way here. So any 2 points connecting this is a cycloid. So you invert that. So it's sort of a nice. Another thing that happens is that most of these problems, it's like the Lagrangian. It is usually easy to do the functional derivative. As we have done almost every problem you can do, it is exactly like a derivative. Give me a function, I will give you the functional derivative. Give a Lagrangian, it's easy to write the Euler-Lagrange equations if you're familiar with that terminology. We will study that, but if you've seen classical mechanics before, you can find the equation, but then the idea is that can you solve those equations? Like, can you solve those differential equations? That's usually not easy, and very rarely you have exact solution. So this is one of those problems that has a solution. Okay, so I'm seeing that's my homework page. So Thursday, and that will be 7 to 10. And there's a midterm coming up. So next week, Thursday is the midterm. seems like it will be mostly on functional derivative and the problems associated with that. And probably by Tuesday we will begin Lagrangian, but then we won't have much. So whatever we do until Thursday can be what will be there. No, let's stick to Tuesday. We'll do whatever we do until Tuesday. It's going to be there in the exam. But I don't know how many examples I will do. But mostly it is going to be examples. The main idea is functional derivatives and it will be applications of it. And also leads to what are the problems you can do using these functional derivatives. One is we started talking about what's called geodesics. These are broad classification of problems. What are geodesics? One of the problems you did in your homework, which was due on Thursday, correct? So pick a surface, like a flat surface is easy, and the constraint you say is that you'll be on the surface. And pick any 2 points and you ask what's the shortest path to connecting those 2 points. And on a surface of a plane, it is a straight line, we all know that. But very quickly, you can ask what is the shortest path on the surface of a sphere. Right? That's also a geodesic, and that's what we will do. That's the first example we will do. What's the shortest path on a sphere? What's the shortest path on a cylinder? What's the shortest? Pick your surface and you can ask what's the shortest path. It doesn't have to be simple geometries like parabolic or ellipsoid, all those. But as you will realize, these are differentials. You need to solve differential equations to get the solution. Not every geometry has a nice simple, it doesn't lead to simple differential equations that can be solved. And we will do that for a sphere. It comes out reasonably easily, which is not surprising. So the sphere is a studied geometry. So that's one class of problems. And you can also change, let me first, so that's first one, right? Second is called brachistochrone problems. So here you say that under gravity, so now whatever you did for geodesic, you have a surface, whatever happens, but now you introduce gravity in it. So geodesic plus gravity. It's like very similar. Here you have to go from one point to the other, but now you have introduced in gravity also. And then ask the same question, what's the shortest? And that is an optimal path in there. Like there are nice questions you can ask. For example, so have you, like you guys must have heard about this. So there's Earth is a sphere, so solid sphere. And suppose you were to make a tunnel, hypothetical tunnel, you cannot make a probably, at least we don't have the technology to build a tunnel going all through the center of the sphere, go there, and then you jump into the sphere. How much time does it take to reach the other side? 3 minutes. Yeah, I like to say 42 minutes, round it off that way, I think because 42 is a popular number in physics. Are you familiar with the 42 number of physics?
Yes.
Yeah, you're familiar. So
You answer to life, the universe, and everything.
Yeah, so it's a what's a
Douglas Adams.
yeah. So it's a how do you know it?
Hitchhiker's Guide to the Galaxy.
So that is a novel, and it's what satire or how do you put it? It's a comic book, not anything deep in there, but it got very popular among physicists, and it got so popular that if you type on Google, there was a time when if you type Google, what's the answer to life and the universe or whatever that sentence is, it will come out 42. So it's interesting that you go from here and you reach there. but it has units, so it's not a fundamental number. It is 42 minutes, right? So it's nothing fundamental about it, and I don't think it is the reason why we chose 42. So that's 42 minutes to go one way. So to come back, it will take 84 minutes. But that was before 2014 or 2013 or something, when it was assumed that Earth is all uniform. But today we know that Earth is not really uniform. It is more dense at the about halfway, and then it is less dense in the other half. And if you take care of that more accurately, then it doesn't come out to be 42. It is about 38 minutes instead. But anyway, so if you have that problem, so you have this tunnel, you go down, and again you can say that's it. That's one path, right? So, but now you can say, what if you were to dig a tunnel from here, so let's say New York to California, right? Somewhere like this. How much time does it take? Anyone? Oh, same, yeah, exactly. Great, nice. So it's again 42, and in fact, you can draw any 2 points, and it's the same because it's the same harmonic oscillator problem that comes up with 42. But then you can ask, okay, that's 42 minutes, but can you have a shorter path? Like, is there a path which is actually minimal time? So fix your 2 points, let's say New York and California. Let's say you have the technology to dig wherever you want to, then is there a optimal path like this, which takes the minimal path? So that would be called a Brachistov problem. Again, you're confined first you build your space, and then you make, in this case, you're free to go anywhere. The second problem you can say is that, okay, you're confined on a surface of a sphere, but that is gravity, right? And then you fix it again. This is an incline. If you're confined on an incline, but you're ready to move on 2 dimensions, then with gravity, what are the constraints you can put? So geodesic plus gravity makes it Brachistov problem. Okay, is that clear? So that's a class of problems. We will do very simple ones in the beginning, but most of these problems are usually not solved completely. Not everyone investigates this, especially these kind of problems. There is not a significant need to solve them. So most of these problems remain unsolved, and someone picks it up and solves it, and it becomes a nice, cute little problem. At least this particular problem, this 38 minutes, I thought was done by an undergraduate student, I remember, in 2013 or 2014. So that exists, all those problems. And the next next class of problems is called minimal surfaces. And minimal surfaces, as you can think of, take a soap film, and it makes a surface. Soap film, you blow a soap film, and imagine that there is no gravity. So that's so that you don't have to accommodate for gravity. Again, you can have 2 classes of problem where you have gravity and do not have gravity. But if you switch off gravity, let's say you're in space and you have a soap film, and you can ask what's the shape it will take. Probably a sphere, right? Probably a sphere. I haven't solved this problem, but probably it will be a sphere. I think so. And again, what are we doing? You're basically reducing the energy, or which particular surface reduces the energy. That's the question you ask, and that's a minimal surface. I bring this up because in Carbondale we have what is a person who is Alan Schoen. I might have mentioned it before in another course, and he invented a geometry called gyroid. And that's basically, if you ask the same question, do you want to have a minimal surface? Sphere is a minimal surface, but then you ask, is it possible to have a minimal surface? So imagine you're blowing a soap film, and you want a surface out of a soap film, which is periodic. It goes all the way to infinity, but in all 3 directions. So you want to imagine a surface it has to be periodic because otherwise it's just flat, right? You cannot reach all three dimensions. So you have a fill space, but you have only one surface. And it turns out that you can actually do it. It's called triply periodic minimal surfaces. And an example of that is the gyroid. There are many other triply periodic surfaces, and it's called a gyroid. And he is from carbon. In fact, SIU, he did this while he was working for NASA, and he's about 92. He was born in 1924, so 98 year old, and he was pretty active until 2-3 years back. Great, and of course, finally, we will not do all this in detail. This example I will do in class, this I will do in class, but this we will have to skip. And finally, this is the action principle, right? Physics, or what do you call it? Newton's Lagrangian action principle. You can also add a lot of like Fermat's theorem. Also comes in the same. Fermat's theorem is about light in the context of light. So what I'm trying to say is that using the techniques we have learned, we can do all these problems. And each of this is a field in its own. You can have an n number of problems on this. We will highlight a few, but that's all. Like in the homework, we will do a catenary problem. I will do brachistochrone. I will also do geodesic, and that's it. And then we will immediately go into the action principle, and we'll keep using the technique, but it will be mostly concentrated on the Lagrangian mechanics. Okay. Any questions? Okay. So let's do an example, geodesic. So let's call this geodesic on a sphere. On the surface of a sphere, the question is you want to go from one point to the other point on the surface of the sphere. To begin with, we need coordinates, right? When we are on a plane, we say X and a Y. What are the points that characterize or uniquely describe a point on a sphere? It is a latitude and a longitude. Right? So if you think of a latitude and longitude, it's clearly specify the positions of your city, for example. What's the longitude of Carbondale? Latitude, let's say. Let's begin with latitude. What's the latitude of Carbondale? Approximately, yes.
55.
55, that's too large. Probably too big. Yeah, 40, I think. It's about 39, I think. 39. Are you thinking longitude? No, even longitude, we are way far away. The London is 0, right? 39, I think so. Check that. If you question me, I'll check that. Yeah.
Wait, is the equator is 0? Or?
Equator is 0.
Okay.
Yeah. Equator is 0. It's not the spherical polar coordinates we use.
Yeah.
So it is 0, and yeah, 55. I think
No,
would be
50.
yeah, probably somewhere London or even above London. Yeah, London might be 55 or yeah. Because 63 Arctic Circle is 67, I think. 67. That's when the daylight. If you cross the Arctic Circle, the interesting part is that there will at least be one day in the year where sun will not set. At least one day. And if you go for more and more, then there are more and more days. Interesting things. Okay. So we need 2 of them. So latitude is 0 here, and that's 90 degree minus 90 degrees, right? But we want to use spherical polar coordinates. So this is in spherical polar coordinates, you say this is your z, that's your x, and that's your y, and you would say that's a vector, right? And that's your angle theta, right? And that's your angle phi. Is that clear? Yeah, this way. Because the projection I'm making. Theta goes from 0 to pi. This is the north pole, that's the south pole. And phi goes from 0 to 2 pi. So really, phi is the longitude. Phi is the longitude. Same thing, same idea. And 0 corresponds to London. Right, that's how. How far does it go? Yeah, quiz. When did longitude first come up? Probably, I would think surely when British were in power. So probably I would think 14 when the sea voyages started. But maybe it has a longer older history. Okay, but latitude is not really theta. So latitude that we use to describe the position on the surface of a sphere is equal to when it is 90, it should be 0. It is 90 minus theta, right? Pi by 2 minus theta. Right? If the north will be 90 degrees, then it is 90 degrees. That's pi by 2. So it's straight forward. So the idea is that there are 2 points, theta 1, phi 1. Any 2 points, theta 2, phi 2. And you want to ask out of all possible spots on the surface of the sphere, which was the shortest. You begin by describing a small line element, so ds square. So this is a small line element on the surface of a sphere. Use spherical coordinates, and we are fixing. So in general, in spherical polar coordinates, you will have dr square plus r square d theta square plus r square sine square theta d phi square. I gave this as a quiz problem, right, to motivate this. So now it should be clear that we can actually draw a tiny rectangle there and how the length comes about. So, so is that clear? Should I describe that? Is that will that help? Okay, quick. So pick a cone.
I think for the quiz, you did not have the dr squared.
Yeah, I did not have this. So I was just asking you guys to do this actually. Yeah, that's correct. Yeah, I'll kill that very quickly. So that's a simple circle, and okay. Okay. It's a cone, and you can actually stretch this out. You see the cube in there? Roughly, yeah. So this is dr. That should be clear. That's the radial outgrowth in there. This is the angle theta, so that's the vertical direction. So that's angle d theta. But this is r. That's the radius of the sphere. That's r. If this is r, this is d theta. That's a part of a circle. That should be r d theta. This will be r plus dr, but double we neglect, right? So this length is r dr, r d theta. This is dr. So that's dr, that's r d theta.
Next question is, what is this piece here? And that comes from this circle. And you notice that this is not part of the circle. Instead, you have to take a circle here. So if you were to draw a sphere like this is coming from this triangle. So when you say d phi, it is part of a tiny circle that is perpendicular to the z-axis. Is that clear? So it's like this. That's your d phi. So if you want that, you want the radius of this piece here. You have to go here and get the radius. So you would say that, oh, if this is d theta, this is theta. So it's r sine theta, the radius of that circle. So the radius of this circle. So if this is r and this is theta, that piece here is r sine theta. It is part of the circle. So this circle is actually horizontal. And there, so it is the radius of that is r sine theta. And r sine theta d phi. So once you have the circle, then the arc length is r sine theta d phi. Is that clear? Or I was too hand waving?
Will it help if I repeat it or? Yeah, okay, keep it as a quiz. That's it. I think you should try to get this. Right. Try to motivate this. Why is it or something?
Okay, we are on the surface of a sphere, so we don't change dr. That's here. R goes away. And let's say that r is the radius of the sphere itself. So that's here r. So this changes to r. Just so that we have a length scale. And that's your length. An arbitrary path on this would be L, and it will depend on theta and phi. So this will be equal to integral of all these arc lengths, right? Add up all these tiny arc lengths, and you go from theta 1, phi 1 to theta 2, phi 3. But now we have to specify the problem. What are we looking for? When we say that we are interested in the equation of the path, what are we asking? In xy plane, you would say, give me the function y as a function of x. Here you would ask, either I have two variables in xy plane, usually it is standard to keep x independent and y as dependent. But now you have two new variables. There is no such strict thing as to whether phi should be independent or theta should be independent. You can think of theta as a function of phi or phi as a function of theta. And both should give the same answer, correct? Whether you do one way or the other. But it turns out that in these kind of problems, I said that when you get a differential equation, it's usually trickier to solve them, or in this case, it is trickier to rearrange them. So if you do this, usually if you use it, I will try to point out how you read this out, which variable to take. In this case, it will be easier if you take theta as the independent variable. Notice phi could be a function of theta. That's one possibility. And theta could be a function of phi. Both are perfectly fine. We will do this. This is simpler. Like basically what it means is that you do the functional derivative and it will come out to be a 0, and immediately you have a linear differential equation. This will lead to a second order differential equation, which of course can be converted into the first order, but you have to do a little more processing in there. So due to that reason, we will have this as our approach. Okay, so that's what it is. So that means that I have to write ds in terms of phi. So then I would say I would like to say this is r. The theta is the independent variable, theta, and then you write this as a square root, right? And this is 1 plus sine square theta. So that's your so substitute that in, and from that point on, now that's where you start doing the functional derivative. Right? You have phi, so immediately you have, and at this point I don't need to write 2 because I've decided that theta is my independent variable. So I'll go from theta 1 to theta 2 or theta. This is 1 plus sine square theta . Right, we start with the construction of the problem, then this is what we want to minimize, which means that I will take the functional derivative. Okay. So add up all the lines, that's the idea of geodesic. And if it was another problem, for example, if it was bracket structure on what are you minimizing, it's again the time, but then you use the energy to you solve for the velocity and you solve for the time. Okay, so so geodesic clearly the geodesic. I'm interested in a geodesic on the surface of a sphere. That's basically variation of L with respect to phi as a function of theta should be equal to 0. Right. That's my definition of a geodesic. So if I do this, set that equal to 0, and that's pretty much what the idea is. This is going to be theta, so it's good to start writing this as theta prime. Right, that is theta. Get clear, the statement of the problem should be clear at this stage. Okay. Do the functional derivative, I'll do the short method, right? You just pretend that this is normal derivative and proceed. Right. So delta L phi over delta phi theta will be pretend that this is normal derivative. So this is equal to, it gets inside, of course. So this is theta 1, theta 2, or theta prime. This is a square root, so I have to do 1 over 2. That's the power of the square root. And when I take the square root, it is 1 by 2 minus 1, so it comes in the denominator. This is 1 plus sine square theta prime phi over prime square. And then hit the argument. I'm hitting with respect to phi. There is sine square theta, does it have a phi? So there is only one phi there. So this is sine square theta prime. And there is 2 times the phi d theta prime. And finally, I reach the point where I have to take the derivative of phi itself, which I will write that as d theta prime. Until now, it was all simple derivative, and now I say this is delta of theta prime over, which is my delta function. Is that clear? Any questions in that? Now that you've done the homework, it should be very clear what's going on. You could do, if there is any confusion of all this, is this really true? how can you use normal derivatives? Then you use this long method and convince yourself that no, this actually works. Factor of 2 cancels out, and that's delta function. This is 1 into 2 of theta prime, and that's sine square theta prime theta prime over 1 plus. And this is the theta prime, and our idea was that this is delta function. Theta and theta prime. It's a derivative of a delta function, which means that the solution will have take the derivative on the other side, everything else, and with a negative sign, and that's it. So that's equal to, oh, I should also, so after oh, this is a delta function, right? It should not affect, yes, so this is R theta prime sine square theta prime P5 and this whole thing evaluated at theta prime is equal to theta. That's what the derivative. Whenever we do this derivative, there is this interpretation that things survive at the boundary, and the idea there is that at the boundary we are not making any change. You're not making any variation in theta or phi at the boundary. So we are saying that delta variation at boundaries is 0. Otherwise, there will be 2 more terms in there. That's what I'm trying to point out. And most of the problems we'll do will have this feature, except when we do conservation principles in the Lagrangian, we will see that it has a lot of richness in there. Even the boundary terms have that neat feature. Okay, so that's your functional derivative. Notice pretty much one step, right, in a sense, and then you have your equation, right? Now you use the idea of geodesic. Geodesic says that this should be equal to 0, that you want to minimize that. So that means you set that to 0. If you set that to 0, that's a total derivative. And set that to 0, you have sine square theta d5 phi d theta and square root of 1 plus sine square theta phi by d theta square root is equal to a constant. And it's a dimensionless constant, right? The way it has shown up. The R goes away, and there is no dimension in this, so C is dimensionless. Did I get this all correct? There's a minus sign. Oh, there's a minus sign here, right? Yeah, thank you. There's a minus sign in there. That's important. That's minus sign. Thank you. But here I can forget that because it was good. Yeah. Anything else I'm missing? Okay, so that's your. So basically, this is a differential equation usually, and that can be simplified. Let's collect all the d phi by d theta in one place. So square this up. So square it up. So it's sine 4 theta. Apparently. Squared. So this is c square plus c square sine square theta
d phi by d theta square. Bring it to the left so that you have d phi by d theta common. So you have d phi by d theta is equal to c square, or I take a square root, right? It's c divided by I can take sine square theta common. Then I take a square root, so sine theta. And there is sine square theta minus c squared. So I think I did it in my head a few steps. So, check. Okay, got the signs correct. That's the larger one, the smaller one. So that's a minus c squared. Then I think so. And we want to solve this. If we want to solve it, it's already theta is on the right side, so we try to integrate this. So that's our goal. Integrate it. So we have d phi is equal to, and let's be simplified. So yeah, there might be shorter ways of proceeding, but let me. Yeah, but there is this extra sine theta, so I think I have to do this. Not sure. Okay, so let me write this as c d theta. This is 1 over sine theta will be cosecant theta divided by actually cosecant square. Yeah, I can pull out a, so this is also c over c cosecant square theta over 1 minus c square. I'm writing it so that I can use the idea of cotangent theta, or the tangent theta integral is typically doable. That's my way of, that's the way I'm going at this point, but that might be shorter. It's out there. So this is 1 minus c square cosecant square. And cosecant square, right? So, because I pulled out one more sign there. Still, I want to process a little bit. I'm not ready for processing yet. So this is c d theta cosecant square theta. Remember your trigonometric identity that 1 plus cotangent square theta is equal to cosecant square theta. I want to use somehow the cotangent piece in there. So use that. So 1 plus. So this is equal to 1 minus c square minus c square cotangent square. Which is the same as c theta cosecant square theta divided by a lot of c, that cancels out. And
define 1 minus c square over c square as c bar square. Sure. Okay. Okay, I think so. Let me try. Cotangent theta is equal to c bar t. Then I have derivative. What's derivative of cotangent theta? Is equal to minus cosecant square theta d theta. I think that's correct. So that's the idea that you have to get this cosecant square theta. So this derivative of cotangent theta. Okay, so this is minus cosecant square theta d theta is equal to c bar dt. That's equal to, okay, I will integrate also somewhere here. This is d5, and I have to integrate. This is going from phi1 to phi2, and this is going from theta1 to theta2. So that's phi2 minus phi1, and this integral now goes from we'll keep this indefinite for a moment. So this is cosecant square d theta is minus c bar e over c bar square minus c bar square square. Yeah, that's minus integral dt over 1 minus t squared, which I think is doable. Okay, here's the quiz. Is there a shorter method to solve this integral? Because I'm doing it in a one way, so attempt on a shorter method, but again, it's a quiz. Don't spend more than 5 minutes. I feel I'm going in a circle. All right, switch over and then I get back and trigonometric one, but probably it's necessary because of the C. That's fine. So the question is repeat with less steps. You can also use tables, right? Integration tables are perfectly fine, but then wrong. So immediately. Okay, what is this answer? Okay, well, we need to put this limits also here. Now we have t, right? So this is cotangent theta 1 over c bar, and this is cotangent theta 2 over c bar. Same thing, here's cotangent theta 1 over c bar, cotangent theta 2. That's integral. Now can be used, we can use simple relations. So we say this is simple theta, right? T is equal to cosine theta. Then dt is equal to minus sine theta d theta. But the denominator itself is d theta. So this is minus of, I'll switch back to theta in a minute. dt is minus sine theta, d theta, and you have 1 minus cosine square theta. That cancels out immediately, and that's d theta. Maybe I should be careful. I shouldn't use theta here, right? Because theta had some meaning there. So new variable alpha. So I shouldn't use theta. That's alpha. Alpha. That's better. So our solution is straightforward. Phi2 delta phi actually. Change in phi is change in alpha. Simple. Alpha 2 minus alpha 1, or let's say alpha, where you take the limits. But now you want to switch back alpha in a sense, right? So, so it is cosine inverse of, actually it will be better if it is the other way, right? I can do this in two ways. Let me give me a second, sorry. Change of fonts. I can substitute the other way also. T is equal to sine alpha. dt is equal to cosine alpha. Then I have the integral of dt is cosine alpha d alpha over 1 minus cosine square alpha 1 minus sine square. And again, that cancels out, and you have minus alpha evaluated between theta 1 and theta 2. So you first convert alpha into theta 1 and theta 2, which is the same as saying this is theta 1, theta 2, which is sine inverse of t. Alpha is sine inverse of t, evaluated between theta 1 and theta 2. It will return back to our old coordinates, but now sine inverse of t, where am I? So that's here. Right? So you want to convert this t into back into cotangent theta. So for that, what I do is I bring it back here, sine inverse. So this is the same as saying sine of phi 2 minus phi 1 is equal to t evaluated between, so this will be cotangent theta over c bar evaluated between theta 1. Is that still visible? Okay. Probably going in long, but each step is trivial, hopefully. Let's get to that. Okay. We'll proceed. So C bar sine of phi 2 minus phi 1 is equal to oh, this one? You did not get this. Oh, maybe that's why I'm stuck here. Okay. So what did I do? So until here it's clear, right? So this is d phi is equal to d alpha, right? So we are saying that d phi is equal to d alpha, right? And then I say that that means phi is equal to alpha plus a constant, right? Yeah, I think that's fine. Point. I don't want this theta 2 roaming around. Yeah. So, okay, maybe your question is correct. Okay, so this is phi is equal to alpha plus a constant then. And now I substitute alpha back. That's equal to phi is equal to sine inverse of t plus a constant. This c is different from original c. So let's say c3. Agreed? And now substitute back. So you say, what is C3? So I say that, okay, at time t equal to, at some variable t, I'll call this C3. So let me call that constant phi naught. So yeah, let's say this is phi naught. Okay. Phi minus phi naught is equal to sine inverse of t. That should be okay. And then I say that sine of phi minus phi naught is equal to t, where t is cotangent theta over c bar. I think that's better. Does that answer your question? I didn't. So you were asking why this is the case. So I think, yeah, what is wrong in this? Yeah, now let me come back and say that, okay, what was wrong? Why did Aryan raise a question? I think the point here is that I'm having two integral constants here, right? I put phi 2 minus phi 1 here, and I'm carrying out this theta 2 minus theta 1 also here. In this way of doing, I've collected all the integration constants in phi naught, right? So that I have only theta and phi remaining here. So here I was doing actual limits where phi 2 minus phi 1 and theta 2 minus. So two integrals, two definite integrals. Not really wrong, absolutely wrong, but at this stage, it gets hard because now I have cotangent theta 2 minus cotangent theta 1. In this case, I've collected all the initial conditions on phi naught. Right? In that sense, this is slightly simple. You see my confusion that I asked to raise myself and which I didn't point it out, I think. So this is reasonable. Okay, this was less number of steps up, I suppose. So if you agree with that, any questions? Yeah. Yes.
You lose the minus sign from the.
Oh, did I lose some minus sign? Because there was a d phi was equal to minus d alpha. This one, correct? Yes, that's correct. And this one I can say minus alpha. Phi naught I can keep the same. Alpha was sine inverse of t, so that's minus. And that will be minus. So this will be minus t, I suppose.
We could just carry that.
Okay. So losing time. Almost. Okay. Write this slightly differently. So this is c bar. Cotangent theta is so this is the same as in c bar sine of phi minus phi naught is equal to minus cosine theta over sine theta. And like before that, I should say our goal was to get a curve which is a function of phi, right? So at this stage, I have that curve if you want. So this is theta is equal to cotangent inverse of c bar sine of phi minus phi naught. Right? That's your function. But whatever that means, but then that's why I'm going to process this a little bit so that we have a little more intuition of what this function is. That's a solution if you want. This function is the minimal solution.
Isn't there a minus sign in there?
Oh, and a minus sign in there because I put this back in here. Yeah. Yes. Yeah. Thank you. Yeah. Did I miss anything else? Sorry, I'm scattered a little. But okay, so now let's see this, what it means. This is the same as C bar sine theta sine of phi minus phi naught is equal to minus cosine theta. That's an equation. Yeah. I'll pull this to the left and expand this out. So I have C bar times sine theta, sine of phi times cosine of phi naught. Next one is C bar sine theta times cosine of phi times sine of phi naught. And pull this on the other side, so it's cosine theta is equal to 0. Remember, I can think of a unit vector R as sine theta cosine phi hat plus sine theta sine phi j hat plus cosine theta. And let me define another unit vector, probably a unit vector, but I'm not sure. So let me say n. I'm not sure if it is a unit vector or not. So the other one will be, this was one, this is minus C bar sine of phi naught hat plus C bar cosine of phi naught j hat plus 1, I suppose. Yes, it is not really a unit vector, right? So, and if you notice this statement, which is the statement of this equation, this function is basically saying that our hat dotted with n is equal to equal to 0. Okay, so which means that this is an equation of a plane, right? Whenever you have this, what you're saying is that all, so if you think of theta and phi as the independent variables, or this can be thought of as x, y, z, right? So this is the same as us. So this is equal to x, xi plus yj plus zk hat over the distance part, right? It is basically a general position, and then you have x times this, x, y times this, plus z times this. That's the equation of a plane. And like, yeah, maybe I could write it like that. So in that way of writing it, I can write this as, yeah, so let's say this is my x, x naught, this is my y naught, and this is my z naught. And that's my x, y, z. So what my point is that there is an equation we have, that this is x plus x times x naught plus y times y naught plus z times z naught is equal to 0. Where our hat is your xi plus yj plus zk over and this is your x dot I. In general, an equation of a plane is a constant. It's a constant that's equal to 0. That's the equation of a plane, but this is a special plane in the sense that this is equal to 0. What that means is that x equal to 0, y equal to 0, and z equal to 0 is on the plane. This means, this implies that x equal to 0, y equal to 0, and z equal to 0 is on the plane. That's the only important piece you want to capture and all that. It's like that's your solution, but I rewrote that equation as an equation of a plane and concluded that this point x equal to 0, y equal to 0, z equal to 0 is on that plane. So now what does that solution mean? Think of a plane cutting the sphere, right? And that plane should be going through the center of the sphere. Right? That's the great circle. Right? Now draw a circle on that. Like it is a circle. How do I know it's a circle? How do I know it's a circle?
Just because we're confined to the sphere.
We can find.
Or it's like, just because we have a plane intersecting a sphere.
Oh, yes, a plane intersecting a sphere will be a circle. Has to be. Yeah, that's correct. Yeah. So it's a circle because it's a plane intersecting a sphere, and it's a great circle because it passes through the center of the sphere. So we know that. So this implies that it's a great circle. So next time if you are flying a plane, you go on a great circle. If you want to say if you want to explore, and you go. That's okay. Sorry, I took a long way. I feel this can be shortened, so that's this. Anything that is hard, I give it to you. But I think there must be, I went around in circles.
No pun intended. You went around in circles.
You want more circles?
No, I said no pun intended, that you went around in circles.
Oh, yeah. Circles, yeah, good. Exactly. Yeah, I will do one more example. I think we can proceed at this stage and start doing classical mechanics, but I think I will prefer to do brachistochrone also. I think when I was designing the problem, my goal was that you should see brachistochrone because it's such a classic problem, but then I missed doing it in the homework. It gave some other problem in the homework, so I had to do it in the class. And so I use a lecture when we have already lost 2 lectures. But I will Any other comments? I think that's already time. I will stop the function. Okay, thank you.